Okay, so we're gonna go ahead and get started just because it's a lot of stuff. So you have a nice definition there. We're gonna talk about divergence and curl, and you can see that there are our learning objectives and the first definition. So I'll give you a couple of seconds while we hopefully wait for some others to join us. All right. Okay, let's get started with example 1. All right, so it says calculating divergence at a point. You can see the following information that they give you. So what we're going to do is some partials. Oops. Right. So then for the divergence at the given point. Sorry for my stutter there for a minute, guys. Not normally my thing. Oh, okay. So if F represents the velocity of a fluid, then the more fluid is flowing out than flowing in at the point. Because we will get a 4 here. My goodness. Okay. So we know that these cancel out. So that's how we get the 4. Okay. All right. Hopefully you're all good with that. And if you were late and you missed it, you can get it off the video later. But that's basically the end point. So determining whether a field is magnetic, is it possible for the following to be a magnetic field? So if F were to be magnetic, then the divergence would be 0. So first we have to figure out the divergence. Okay. Then we'll have 2xy. Sorry, my 2 looks like the 2 up there, or the not 2 up there. Guess I'll use the other way of writing it too. It's 1 minus 2. See, it's hard for me because no matter which way I write a 2, it either looks like the not 2 up top, or the or like a Z. So like I can't do either. So since 1 is not 0, therefore F cannot model a magnetic field. Okay, and then we have this nice little visual aid. Okay. Alright, so we have some theorems. I was nice and I gave you the proof in between, so this proof goes with this one. Right. Well, I feel a little bit better that we're already on 5. I just saw 17 pages of my own notes and was like, oh, it's gonna take us a minute. All right, determining whether a field is source free. So is the following field source free? So what we need to note is that the domain of F is R squared, which is simply connected. Furthermore, F is continuous with differential whole component functions. So because of that, then we can use the divergence test for source-free vector fields to analyze F. So because of those two things, we're going to do the following. And that will give us 2xy minus 2 xy, which is 0. Okay. So therefore, F is source free. And if you want to be most correct, you would say by divergence test for source free vector fields. Okay. All right. Determining flow of a fluid. Pose the following. Models the flow of a fluid. Is the fluid moving into point 1,4, then flowing out? So we have a vector field. I believe I can show it to you now. I'm gonna assume I can. All right. So to determine whether fluid is more flowing into than out of, we have to calculate the convergence of V at 0.14. So we're going to get negative y plus 1. And then now if we substitute in the 1,4, we're going to get minus 4 plus 1, which is a negative 3. Since the divergence of V at 1,4 is negative, more fluid is flowing in rather than out. All right. So you have a nice definition of the curl that I guess we can see in a moment if that is presenting an issue. Oh no, you guys know I don't have all calculation hours, so hold on. That's just also causing a problem. Try using the opposite sign there. So this and it works out correctly. Nice. All right, so here's how we'll play that. More than likely, probably not going to include it on the final. So, get through your homework with it. And we will work with it on the examples here. Sorry, definitely work your homework out. We'll see what happens. You guys might want to try like checking out some other YouTubes. Maybe they explain it in further detail. Maybe they'll have it correct, or at least explain the proof behind it. That would make a big difference. Okay, so here let's try what they want us to do. So in this one, they just want like the write-up. They don't want the answer. So by that, I mean they just want you to do curl F equals delta cross F. So I, J, A, partials. Sorry, that's a Z. And then P, Q, R. So that's going to be RY minus QZI plus PZ minus RXJ. Again, we don't know if this why this J term is becoming negative, but I guess for your homework, try it that way. And then QX minus PYK. So then what we end up getting is XZ minus XI plus X squared minus YZJ plus ZK. That's all I want for that one. You don't have to go any further than that. Okay, so finding the curl of a two-dimensional vector field. All right, I think I can show you this now. Hopefully it's not going to be like, surprise, the answer. But it is not. It is all good. Yeah. Notice that this vector field consists of vectors that are all parallel. If you couldn't pick up on that, I'm sorry. In fact, each vector in the field is parallel to the x-axis. To x-axis. This fact might lead us to the conclusion that the field has no spin and that the curl is 0. To test this theory, note that so we would have curl F be QX minus PY K equals a negative K, which is not 0. Therefore, this vector field does not spin. Oh, we're going Christmas. To see why, imagine placing a paddle wheel at a point in the first quadrant. The wheel rotates. The larger magnitudes of the vectors at the top of the wheel will cause the wheel to rotate. The wheel rotates in a clockwise or negative direction, causing the coefficient of curl to be negative. Okay. All right. Determining the spin of a gravitational field. Show the gravitational field has no spin. Show that the field has no spin. We calculate its curl. So we want to let P, X, Y, Z equal to X over X squared plus Y squared plus Z squared to the 3/2. I thought that would be the only one we would have, but guess not. Then we have Q, X, Y, Z, which is going to be the same thing, but a Y on top instead of an X. So that means if you write faster than me, you know what the last one is. Oops, 3/2. All right, so then that tells us curl F equals negative G M1 M2 it's gonna look crazy. Just so you're all aware. And we only get one extra slide, and I'm pretty sure I need it at the very end. I think I'm gonna try really hard not to write super duper duper big. Oops. Okay, so then we gotta plug in all of our stuff that we just found. For this, no, I can't do that. I can't just skip that. I gotta write it out. Okay. So negative 3x, nope, 3, negative 3 yz over x squared plus y squared plus z squared to the 5/2 minus yep, negative 3 yz over x squared plus y squared plus z squared to the 5/2 I minus 3x z over x squared plus y squared plus z squared to the 5/2 minus negative 3xz over x squared plus y squared plus z squared 5/2 j right, and then minus 3xy over x squared plus y squared plus z squared the 5/2 minus negative 3xy over x squared plus y squared plus z squared the 5/2 and that's got the k with it, and you finish off the square bracket. Okay, you complete all of that and your answer will be 0. Right? Since the curl of the gravitational field is 0, the field has no spin. Okay. There we go. Okay. So we get back to our this part. So you can use a negative if you don't swap the partials in J. Does that help everybody? Okay, hopefully. Hopefully that will help. That makes some good sense. Okay. Here is our next theorem, and I give the proof. I was nice. It's also in your textbook. Okay. But it is nice to know that you can use either approach. So, all right. So for the homework, use the negative. Although that's interesting that if you swapped it and did it correctly, I would think the answers should come out the same. But if Seth's already done some of the homework, I would recommend just using the negative option. But you can also go through and do it the other way. You can try not doing the swap or doing the swap. All right. Showing that a vector field is not the curl of another. So we're given a vector field F, and we need to show that the curl of another vector field, that is, show that there is no other vector G with where it would be equal. Oh, sorry guys. Oh, I'm finding a very bad headache. All right, so here's what we want to notice. The domain for F is in 3 space. The second order partials of F are all continuous. Hopefully you guys know how to spell that word better than me. So therefore we can apply the previous theorem to F. All right, so the divergence how did they do it that way? Like that? So then that would be e to x plus z plus 2xz. If F were the curl of vector field G, then we would see but the divergence of F is not 0. Nice. So therefore F is not the curl of any other vector field. All right. Good stuff today. You guys are great. Seeing you guys all eat a little bit of turkey and come back with great brain thoughts. And I did mention when folks were still kind of coming in, I went ahead and reopened your first 4 sections. Right. So again, I give you guys the proofs. All right, well, obviously I'm failing at a star there, but whatever. Try to get your last 4 sections done. I am gonna try to grade your last test. I'm sorry, with the holiday and everything, I just didn't. I assumed I would have more time at home, and I did not. But I will get your stuff definitely done before we review the final. Review for the final. No. And you guys should have, I mean, we're flying through this one, so hopefully the next one's just as quick and you guys can have a decent amount of time to do some homework tonight. All right. Says testing whether a vector field is conservative. Sorry, not consecutive. Use the curl to determine whether the function is conservative. All right. So here's what we need to note. Oh man, I hope I don't end up doing Christmas again. So again, we're in 3 space. It's simply connected. Because if you look at the figure, there you go. So therefore we can test whether the vector field is conservative by calculating its curl. So not going for Christmas this time. So we would have, oops, that should be Y. X, Y. They actually don't use the parentheses there. Okay. And plus, keep wanting to do an X. Watch, when I need to write an X, I won't be able to. Alright, so then that gives us, I guess we're going a little bit Christmas. Gonna give us X minus X I plus Y minus Y J plus Z minus Z K which is equal to 0. Alright, so this tells us F is conservative. Okay. And more than likely, you probably would have looked at that image and assumed it was conservative, but now you understand why you would have made that natural assumption. Okay. All right. Keep it going. That's confusing. Guess we'll see what the next 4 slides have. I'm hoping it's notes because my questions seem to be done. Analyzing a function. Is it possible for the following to be a potential function of an electrostatic field that is located in a region of R2 free of static charge? Excuse me. So if F were a potential function, Then F would be harmonic. Note that we have the following. Oops. And so that sounds like something a math person would say. And so oops, this is a plus. So therefore F is not harmonic and F cannot represent an electrostatic potential. So nope. Electrostatic, not electromagnetic. I'm making up physics words. Potential. Let's fix that. Okay. I think I remembered what happened, maybe. We might be going directly into the next section. Yep, we are. Because I ran out of slides. So give me a second.